Here we've got an example problem. It's about a cheetah. Let's just say you are here at this point. 20 meters away is a cheetah that sees an unlucky antelope 50 meters away from you. So the cheetah's at 20 meters, the antelope's at 50 meters. And we can describe the cheetah's position once it starts moving, starts chasing after the antelope, by this function here. So its displacement, x, equals 20 meters. Hey, that's the 20 meters lead it has on you, plus 5.0 meters per second squared times the time squared. So the first question is, how far away is the cheetah in 1 second? We already know at 0 seconds it's 20 meters away, but how far away is it in 1 second? So if we know that t1 equals 1.0 seconds, we then can reason that x1 equals whatever t1 is plugged into this function. So 20 meters plus 5.0 meters per second squared times 1.0 seconds squared. Now this second gets squared, right? And it cancels this second squared down here. And I've got meters left over. If I add those up, I should get a meter again for x. And 1 squared is 1, times 5 is 5, plus 20 equals 25 meters. T2 is 2 seconds. So that means x2 equals the same function, 20 meters plus 5.0 meters per second squared. Now this time, t equals 2. So put in 2.0 seconds, we square that. These seconds squared cancel. 2 then becomes 4. So 2 squared times 5 equals 20, plus 20 equals 40 meters. So that's the cheetah's position after 1 second and 2 seconds. What's the cheetah's average velocity from t equals 1 second to t equals 2 seconds? Well, that's easy enough to do because we know average velocity in the x direction equals delta x over delta t. Well, we know from up here it's going to be x2 minus x1 over t2 minus t1. And x2, we discovered, is 40 meters. x1 is 25 meters. And t2 is 2 seconds. t1 is 1 second. That's going to equal equal 15 meters per second. Easy, just like last time. Let's ask ourselves, so how far away is the cheetah? Say cheetah's average velocity. The next question asks us, what is the cheetah's average speed from 1 second to 1.1 second? And then it's going to ask us from 1 second to 1.01 seconds, and then 1 second to 1.001 seconds. So the time interval gets shorter and shorter and shorter. So we're going from an average velocity over 1/10 of a second to really nearly instantaneous velocity over 1,000th of a second. So we'll plug that in. So we already know at 1 second the cheetah is at 25 meters away. So we're going to use that. The question is, how far away is he at at 0.1 seconds. So we have to figure that bit out first. So it's going to be x2 minus x1 over t2 minus t1. So x2 equals 20 meters plus 5.0 meters per second squared times 1.1 seconds squared minus 25 meters. So x1 is 25 meters, x2 is his position at 1.1 seconds. So this is x2, this is x1. So t2 is 1.1 seconds minus 1.0 seconds for t1. That's going to equal 10.5 meters per second. Now we go ahead and repeat this exercise with 1.01 seconds. So here becomes t2. 25 meters is still t1. x1. x2 is this expression with 1.01 seconds plugged in there. 25 meters is x1. The time at x1 is 1.01 seconds. And the time at 25 meters is 1 second. Well, if we put that in, it calculates to 10.05 meters per second. Then we can look at 1.001 seconds. The first expression is where the cheetah is at 1.001 seconds, which is described by our function that we were given here. And then we subtract the 25 meters, which is x1, which is where he was at 1 second. And so as you can see, as we take smaller and smaller chunks of time, we get down to about 10 meters per second. So as we can say, then as delta t approaches 0, v equals about 10 meters per second. Now that's the hard way. Let's do it the easy way. And this is usually what happens. It says, write an expression to describe the cheetah's velocity at 1 second and at 2 seconds. Well, we already know that the displacement equals 20 meters plus 5.0 meters per second squared times t squared. So this function describes the cheetah's position with respect to time. But in order to get its velocity, we have to take the derivative. So, velocity equals dx dt, which we can figure out. So here, we don't have a t. There's no exponent for us to subtract. So what happens is really, this is like, we could also say this is t equals 0. Oh, pardon. Yeah, t equals 0. So what happens is, this drops out and becomes 0. So we don't have to worry about that one. Here, 2 times 5 is 10. Keep the t in there, and we subtract 1 from the exponent to keep it 1. So therefore, velocity equals 10t. The units don't change at all. So really, what we have here is velocity 1 equals 10 meters per second squared times t1. And v2 equals 10 meters per second squared times t2. So if t1 is 1 second, v1 equals 10 meters per second squared times 1 second. This second cancels out that square, and our result is 10 meters per second. In this example, v2 equals 10 meters per second squared, and now we're going to substitute in 2 seconds. This s cancels this, and our answer now is 10 times 2, or 20 meters per second. So, that's how you calculate the instantaneous velocity. But there's one more thing in dealing with graphs. In this graph, we had the acceleration. We had the plane going down the runway. And if we graph x versus t, we see that the slope gets steeper and steeper and steeper as the plane is going further down the runway, which means it's going faster and faster and faster. But what if we have a more complicated function? Maybe one that looks like this. Here we see the velocity is increasing slowly. Here, it's going very fast. And here, it's flat. And here, you can see the line is going down this way. So think about that slope. And then over here, it flattens out again. A common question is to ask you, where is the velocity the least? Well, here, where is it greatest? Well, it's greatest here because the slope is steepest. So we would say that the velocity is greatest at point B. So B is greatest. Now, where is the velocity, instantaneous velocity, the least? Well, here it's less because it's going like this. Up here, the slope at the top, this is an optimum, right? So that would be 0, v equals 0. Here, this is also flat, so v equals 0 here. So now you're kind of stuck. You choose C or E. Well, you don't, because what happens is the velocity here at D is negative. So at D, v is less than 0, which makes that the smallest one. So remember, we were going from our home to the Kennedy, and then we turned around to go back. And so our velocity going toward the expressway was 30 kilometers per hour. But then we turned around and went back, and our velocity was negative 30 kilometers per hour. So 30 kilometers per hour from home to the Kennedy. But then we went back this way, and it was negative 30 kilometers per hour. So you can learn a lot about complex motions by looking at a graph of their function. So there you go. There's physics and calculus.